All right, one last example of how intermolecular forces relate to physical properties. I'm going to go ahead and define melting on a particle level. You guys know that melting is a phase change from solid to liquid, and with that phase change, there's an increase in particle spacing as heat energy is transferred through collisions. And so when we look at molecules and determine their melting points, we can look at the intermolecular forces of attraction between molecules of the same type, and we can rank them accordingly. So the very first thing we'll have to do is look at defining what these are. So I'm going to go ahead and rank these, identify the type of molecule. So aluminum oxide is ionic. Then we have methane. And methane is nonpolar covalence. It has a symmetrical shape and nonpolar bonds. Then we have hexane, which is also nonpolar covalence. We have water, which is polar covalent. We have sodium chloride, which is ionic. And we have phosphorus trifluoride, which is polar covalent. So I'm going to go ahead and rank melting point. Again, melting point would be the temperature at which particle spacing increases and the phase changes. And we're going to go ahead and rank based on intermolecular forces. So the top here would be ion, ion. Then we've got hydrogen bonds. Then we have dipole, dipole, and London dispersion. So with ionic, you can rank based on, again, charge difference and ionic radii. So we're going to go ahead and rank aluminum oxide at the top. In the lab, this would have been calcium oxide. We'll put calcium oxide in there as well. And then sodium chloride. So if you look at the melting points of those different ionic compounds, they're pretty high because the intermolecular force is so great. And then moving down to hydrogen, water forms a hydrogen bond. So that would be the next in the ranking. And then dipole, dipole. Those would be your polar covalent molecules that aren't forming from hydrogen bonds, like phosphorus trifluoride. And then lastly, our nonpolar covalent. And so here you want to look at the size of the molecule and the number of shared electrons. So the stronger attraction between the two, again, both nonpolar covalent, would be the larger molecule with the greater number of electrons. And then the weakest attraction would be the smaller nonpolar molecule. So here you go. We've ranked these based on type of particle, intermolecular forces, and melting point. Hope this helps. Talk to you guys soon.